Okay, so we come to the last segment, which is our keynote to wrap up everything. Let me just get Keegan wired up.
This work? Yeah. Just while they're working on that, I'd like to remind everybody that you can now vote for your People's Choice presenters. So the details for the email address to send your vote to are in the main hall. So if you could do that, that would be great. Thank you.
So to finish our program, it's my pleasure to introduce Keegan Smith from the Curtin Institute for Computation, who'll be giving our keynote from astrophysics research to research software development, responding to a need for a new breed of expertise. Thanks, Keegan.
Cheers. Hi, everyone. I just want to say a big thank you to Xiqing for asking me to present in the first place. Thank you to everyone online who's still here at what could be quite late for you. And thanks everyone sitting down for still being here right before lunch. So yeah, I'm a software developer, a research software developer, and I work at the Curtin Institute for Computation. And when Xiqing asked me to present, I sort of wanted to make something as relevant as I could to a bunch of statisticians, early career researchers. And it took me a little while to figure out how to do that. But to do that, to sort of talk about how I bridge the gap between astrophysics and becoming a research software developer, I think we have to start at the start. So this is the kind of thing that a lot of people might think of when I talk about astrophysics. Like, how could you not? There's gorgeous images. Thanks, NASA. So at the top left, we have an all-sky image of our whole galaxy in infrared. Right next to it is a supernova remnant, which is the leftover bits of when a star explodes, goes supernova. It leaves behind this cloud that looks really pretty. Bottom right, we have a gravitationally lensed cluster of galaxies. This occurs when you have a gravitational field strong enough to warp space-time, and light traces its way around that space-time, and you get the sort of circular pattern amongst all the galaxies. Big thing down the middle, you might all know as Jupiter. You can tell because of the big red spot. It looks kind of funny. It's in different colors because it's infrared. And the last picture to the bottom left is a galaxy merger. This happens when two galaxies eventually collide, and over the next few million years, they're going to do this dance back and forth and merge into one big galaxy. So straight out of high school, this is all I wanted to do. I wanted to just make a bunch of pictures like this, because that'd be just fantastic. I could do that for 40 years and then retire and be happy. I ended up going into a PhD in astrophysics, and what I was doing was none of this stuff. But my project did involve, it did involve itself in the end of a star's life cycle. So when a star ends its life cycle, it finishes up all of the fuel that it's using to perform fusion. When that happens, the pressure that it was exerting on itself to keep itself up stops being there. So it falls in on itself and undergoes what we know as a supernova. And there are a few different scenarios that can happen depending on how big the star is. So we have a small star like our sun, we get this white dwarf, which is just a tiny little thing that shines for billions and billions of years. Not very exciting. Everyone's probably a bit more familiar with the final scenario where you have an enormous star and nothing stops all of its material from continuing to collapse into a single point, which we call a singularity. And this is cloaked in an event horizon in what we all know as a black hole. My project was somewhere in the middle, wherein the star isn't big enough to continue to collapse, but it stops at this really compact, dense star that doesn't shine. We call it a neutron star. But if it doesn't shine, we need to know we need to know that they exist somehow. And there is a special scenario of neutron star called a pulsar. This looks like something like the picture on the left, where we have this really strong magnetic field misaligned with its rotation axis. This makes it look kind of like a lighthouse, so we call them space lighthouses. And when its magnetic axis sweeps across our field of vision, we trace out a pulse, like this, like the lines being traced down the bottom. I hope that looks okay on Zoom. And these things can spin really quickly. The fastest spinning pulsar is quicker than 2 milliseconds. And that's pretty extreme for something that weighs twice the mass of our sun. Most pulsars, however, can't be seen just through their individual pulses. So we can't just trace out stacks like this, lines like this. So what we do is we stack these pulses together. And in doing so, the noise stays noise because you add noise to noise, it's still noise. And the actual signal attenuates. And eventually you get something called a pulse profile that looks like one of these things. First thing you'll notice is that these all look very different. These are 3 different pulsars that I just grabbed from the internet. And all of them have very different morphologies. So on the left, we've got a single main peak with a bit of trail in and out. The middle has 3 peaks, 2 very small ones, but they're significant, so they're 3 peaks. And the final one is dual peaked. So my project was about trying to sample as many different pulsars as we could and see if we can say something about the physical characteristics of the pulsar just from these alone. So now it just became a numbers game, trying to observe as many pulsars as we can, as quickly as we can, and see what we get out of that. Luckily for us, there are quite a few known pulsars already. We can go find them. This is an all-sky map of our sky, where every gray dot is a pulsar that we know about. Can anyone hazard to guess as to what this strip is? You think it's a sample bias? Well, you're sort of right. This is our galaxy. This is the strip of our galaxies. This is us looking into it. You're right that we point our galaxies towards it, but that's because we know that that's where all the observable pulsars are. All pulsars that we've observed are galactic because they're not bright enough to be seen from another galaxy. So if I wanted to observe, say, I think there's about 2,000 points here. If I wanted to observe, say, half that would take an enormous amount of telescope time because the telescope would have to point at each one, observe for about an hour, and then that's 1,000 hours of telescope time. No one in their right mind is going to give you that amount of time. So we needed a way to do it quicker. And this is where Australia's very own Murchison Wide Field Array comes into play. This, believe it or not, is a telescope. It's situated in the Murchison area, which is just northeast of us. And it consists of thousands of these little spider-looking things. So these are really just a couple of antennas put together, because all you really need to observe a radio wave is a piece of wire. When an electromagnetic wave is incident on the piece of wire, it wiggles the electrons in it, and that creates a voltage current you can measure. And that's all we're doing, just measuring current. Because there are so many of these, and they have to record at such a high time resolution, so that we can resolve out the pulse profile, this results in an enormous data throughput. 7.7 gigabytes per second is what we observe. To give you an idea of how big that is, Shrek in HD is about 5.1 gigabytes. So if we have a standard observation of about 80 minutes, that's roughly 7,200 Shreks we're watching every observation. But the good thing about this is that because these don't have a dish or any angling, any way to physically angle the waves, we get this enormous field of view. So that means that we can observe the whole sky relatively quickly. We don't have to ask for 1,000 hours. Now this 7.7 gigabytes per second is also not the final product of the telescope. This is still under construction. It's part of a much bigger telescope that will be roughly 1,000 times the data rate, the order of 10 terabytes per second. But for me, 7.7 was enough. So I started my PhD, and the basic idea was to just download, process, check if I detected any pulsars, and then upload that to our database. And then that will just be my data gathering for a year or so and write some results based on that. This turned out to be quite the challenge for a few reasons. Number one was I didn't know how to write any code. All I had was very basic knowledge from doing my undergrad in physics, how to write a little bit of Fortran, and that's it. But I had my colleagues for that. They were really helpful at getting me up to speed. Learning how to use version control like GitHub was huge. The second challenge was that the devil's in the detail. My initial plan for the pipeline wasn't quite as simple. Was a lot more simple than what it ended up being. Also, after running this for a little bit, I was running this on the Pawsey Supercomputing Center, which is here in Perth. They sent me this email about 12 months after I'd started it and congratulated me on submitting 240,000 jobs, which at the time I thought was fantastic. I'm like, oh, I must be doing really good work. I'll mention later why this actually turned out to be a red flag. So the outcome after about 18 months into my PhD was pretty good. I had doubled the number of MWA detected pulsars using my pipeline and made some software that everyone else can use and I think is still using today, which is great. But there were a few issues. Number one being that we had hit a ceiling in the number of pulsars that we could observe. I'd already observed the whole sky using 10-minute snapshots. This meant that if I wanted to get any more data, I just have to wait a lot longer. We still had 80-minute observations. So if I wanted to get more detections, I could download the whole 80 minutes, but I get a √8 increase in sensitivity. So it's diminishing returns. Additionally, the software that I had written was very brittle. It broke a lot. It wasn't documented very well, which meant that no one else could really use it without me telling them how to. And actually modifying the code to do anything else was hard to do because I just hadn't written it very well. Perhaps the most damning problem was that the software that I had written wasn't part of my PhD. It was a means to an end of the PhD. So the issue with this is that the software was the hardest part of doing it though. So I'd spent most of my time just trying to make something that worked without really focusing on what the results were. And this brings me to kind of the first real point that I wanted to make today. Sorry, it's taken 12 minutes to get here, but data inflation, not the only, there's more than one kind of inflation we have to worry about. The point I wanted to make was that researchers in this day and age need better software skills. So as not to say that researchers aren't pulling their weight. It's not their job to write good software or write something maintainable to be used by the broader audience. It's their job to output results. And that's really all they should be doing. But today, data rates can be enormous. The graph, or the infogram I've chucked up here is a testament to that. And most researchers and academics aren't equipped to deal with like 7.7 gigabytes per second of data. And simple solutions like building a spreadsheet or storing your data on a USB or a hard drive just aren't viable anymore. So I think the first thing I wanted to get to was to give an understanding of what basic software skills are out there, or what maybe a good starting point might be for someone who wants to become a bit more competent in how to create good software and something that will sort of stand the test of time. So the number one thing is best practices. Best practices can be thought of as things that you should or should not be doing when you're writing code. So commenting and writing documentation are grouped together quite often. But I wanted to sort of split the difference and say that commenting is for a different purpose than documentation. Commenting goes in your code, which means that anybody reading your code is reading your comments. So that should be telling anybody who's trying to understand or modify your code how to do it. Documentation is for the user. It's written as human readable as possible. So it's for anybody that plans on using your software or your code to do something, they should know how to do it and what not to use it for. Good code is also both maintainable and dry. Maintainable in the sense that it can be modified, hopefully without breaking everything else in the code. And dry stands for don't repeat yourself. Don't repeat yourself because if you are repeating sections of your code, usually it means that your workflow isn't very efficient. And it's also a very good way to break things in 2 places rather than 1 place. And you have to fix 2 times the things when something breaks. You're also duplicating your effort if you're repeating yourself. And kind of the whole point of writing a program is to minimize effort. Well, you maximize your overhead, but in the long run, you'll be saving yourself a lot of time. One other thing I would consider essential is Bash. Bash is a login shell for Linux and Unix systems, which doesn't really mean anything, but what it is used for, or what it can be thought of being used for is communicating with your operating system through text or typing through a command line interface. I use Bash every day, but I rarely use Bash or the full functionality of Bash because there's usually something better to do all of the complicated things. So if I wanted to write a workflow or something, I wouldn't use Bash. But if I wanted to copy a file, I would use Bash. And that's really all you need to know is like the basics. So changing a directory, copying things, moving around, that kind of stuff. Python. Python is my favorite programming language because I can just write whatever I want. Somehow it works. This could really be replaced with any sort of high-level language, but I think Python is a good teaching point and a very good first language for anybody who wants to learn. Because it's high-level meaning that all of the little underlying things like declaring a variable or managing your memory, that's all hidden from the user. Python does all of it for you. This is fantastic because it makes things really easy, but it also makes things very slow because it has to figure out what to do and what you meant it to do. So Python is fantastic if you want to build infrastructure or short workflows, do some data visualization. It's not great if you need things to run really fast. There are ways to get around the slowness of Python. Packages can speed things up, but usually learning how to make that package work properly is about as hard as just learning another language. So it's up to you what you want to do. Python environments can also get very complicated because they rely a lot on different packages, and versions of packages can conflict, which means that your environments need to be managed by an external package manager like Anaconda. But now it's gotten to the stage where Anaconda isn't doing a good enough job, so you get other things to manage Anaconda and manage Python. So it just kind of keeps, in 20 years, there's going to be a long trail of things that you need to get an environment working in Python. Git and GitHub are great tools that are not to be confused. Git is a version control software, and I'm sure we've all had situations like this where we've made a change to one of our assignments, but maybe we did it wrong, so we should keep the old version just in case. And we do that like 5 times, so we've got 5 different final copies of our assignment. Git removes the need for this because it keeps track of all the changes that you make and allows you to go back if you need to. GitHub can be thought of as a cloud integration of Git. So it's doing the same thing, but storing it all on the cloud. You can access it anywhere. And sort of like a really complicated version of Dropbox. The great thing about this is that you can collaborate with other people on the same project. You can see if your changes conflict with theirs, and you can see when other people have made changes as well. Perhaps the most useful tool of all, Google. I use Google all the time. Don't tell my line manager. If you encounter an error, you are almost definitely not the first person to encounter that error. If you have a question that needs answering, somebody else has probably asked it and been answered already. So use the resources of the internet because it's the easiest way to get anything done really quickly. If all else fails, you can always ask somebody in a forum, and usually if somebody is given fake internet points to answer your question, they're more than happy to do it. The second point I wanted to make is that sometimes just knowing these things isn't enough for people to get by. 7.7 gigabytes was way too much for me as a PhD student. So in hindsight, I think it's too much to expect of every researcher to keep adding to their skill set just so they can output the same result that they might have 20 years ago. And for this, we have dedicated research software developers like me. And we're good for handling all kinds of things. Like, for example, if you need to process an extremely large data set, if you are having issues with your code running slowly, it can be optimized through something like GPU acceleration. If you need a web page, that's definitely not something a researcher should have to make. Large workflows, complex infrastructure, and implementing security are also things that I would flag. And here we are at the Curtin Institute for Computation, which is where I work. We're a facility of roughly 40 people, mostly technical staff, but we've also got a diverse range of admin staff as well. We've got like project coordination, business management, marketing, admin support, everything's there. We also run a diverse range of projects, and I've got all the logos on the right here. So at the top is the project that I work on, the Curtin Open Knowledge Initiative, which deals in all things open access, like open access books and journal articles. Below that, astronomy data and computing services, which is exactly what you would think it would be. And it's incredible that I didn't end up working there as an astrophysicist. Below that is the Australian Space Analysis Facility, Space Data Analysis Facility. AFID for automated fish detection. It's amazing what there's so much need for automating viewing a fish. You wouldn't believe it. Apparently, a lot of fish biologists just stare at computers all day, clicking on fish and telling the computer what fish it is. So we're trying to save like tens of thousands of hours. Milo is a project, stands for Manage Your Life Online, which is a project one of my colleagues is working on, and it's fantastic. It's a mental health service that they're trying to bring up so that you can just talk to a digital therapist online whenever you can. But rewinding the clock a bit, I'm still doing my PhD, but I realized that I wanted to do something else. The most interesting part, I thought, of my PhD was not the science output that I was getting out of it. It was trying to figure out how to make the system as efficient as possible to process that much data. So I sort of thought about what I needed to do in order to enter this realm of software and big data. And the thing that jumped out at me was that you don't need a PhD to do that. You definitely don't need a PhD in physics to be a software developer. So I dropped out. And that was like 8 years down the drain, but ended up being worth it. But at this point, I sort of wondered to myself, what do I do? How do I enter this realm that I want to get into? So I thought the best way to do that was just to learn a bunch of things. I spent about 6 months learning things on Udemy. Udemy, fantastic platform. Would recommend never paying full price on Udemy. You didn't hear it from me, but if you just make a new account, they always give you 80% off. Yeah, I spent a little bit of time learning a bit more about data science, statistics with Python. Also learned about relational databases because I thought that would be a good thing to learn about since almost everybody that I was looking at was using them and I didn't know what they were. I also did all the basic things that, looking for a job. I updated my resume, updated my LinkedIn, and I would never have guessed that updating LinkedIn would actually be useful, but it got me my first job, which was not at the CIC. My first real job was as a junior technical specialist. And the more I think about this name, the more I think it just means does things with computers, which was pretty accurate, honestly. So I worked for an environmental company which was trying to help marine wildlife off the coast of Western Australia, and namely turtles. The issue they were having was that if there is a big mining site nearby and the turtle hatchlings hatch at night, they come out and they look for the brightest thing that they can see, which is meant to be the full moon, because that leads them out to the ocean. If it is instead a mining site, they'll just run towards the mining site and die. So I was helping turtles, which felt pretty good. I also ended up back in the realm of supercomputing. This time I was working at, I was running things on Doug, which is another Perth-based supercomputer. This was also the source of probably the most heinous Fortran code I've ever seen. If you are unaware why nesting 10 for loops inside 4 go-tos is a bad idea, all you have to do is try to change something and figure out what it does. I never figured out what that did. Instead, I just wrote a Python wrapper. This was also the first time that I realized that running things on a supercomputer costs quite a bit of money. It also dawned on me that when I ran 240,000 jobs at Pawsey, someone had to pay for it, and Pawsey is government funded. So I've cost the taxpayer a fair bit of money. I owe you all a pint, sorry. But there was only so much that a small environmental company could offer me in terms of professional development. So I still sort of had this desire to get more into software and data science. I noticed that the CIC was hiring. So I also noticed that I didn't fit all of the technical criteria. There are a lot of things that they were asking for that I'd never heard of before. But I thought, I have a background in research, and I thought that that might be relevant to whatever they're doing, and I could sort of sell myself as this critical thinking, problem-solving kind of guy. I didn't have much hope, but I thought I might as well give it a shot. You know, I had nothing to lose. I also crammed another 40-hour course into 2 weeks, much to the dismay of my social life. But eventually, I handed in my resume, selection criteria, got an offer for an interview, and got the job. Hey. So this is where we are today, working at the Curtin Institute for Computation. Now, I want to talk about sort of my first impressions when I started working, because I expected it to be quite a lot to take on board. And it was. The most challenging thing I found was understanding the scope of the project that I was working on. There are a lot of different moving parts. And the reason it was so complicated, to me at least, was because, one, I didn't really have that much experience, and two, I'd entered this project as a latecomer. It had been running for 2 years, and all of the decisions based on all of the decisions of what platforms to use and what services to use and why we're using them, how they're being used, were made without me being there. So I had no understanding of why things were the way that they were. But my colleagues were really helpful. They've been the world of difference because they understood what it was like to just be entering a new field, not really understand what's happening. They were very patient. So, and yeah, as an attempt to understand the whole project, I made a plot like this. And if you run into the same issue, I would highly recommend doing something like this. It's actually been really helpful. And now I can present it to everyone else. So it gives you some material too. Throughout the creation of the plot, I sort of found myself asking quite often, why do we need this? Why do we need this and this and this and this, all these things? The more I asked, the more my colleagues listened, and they're actually very helpful and gave me a bunch of answers. And every answer I found was pretty adequate. I mean, we use a lot of different things, and it turns out that all of them have a good use and a reason to be there. So I thought I would spend the last 5 or so minutes talking about the things that I use on a daily basis that are sort of staples in my job and why we use them. The first thing is relational databases. Technically, we don't use relational databases, but just pretend that we do, because they're basically the same thing to what we use. A relational database is effectively a set of tables that are all linked by some key, and that makes a relation. So like the example I've shown here, we have a movie table, production companies, and movie earnings. So in the two top tables, you can see that they have, you can logically separate all the information, and they have primary keys to identify each row. In the bottom table, we've made this duplicate pair primary key, which are the movie and company IDs, and we've listed the movie earnings for each one. What this allows you to do is just look at the movie earnings without having all of this bloated information from the movies, for example, and you haven't duplicated your data in that table. SQL is the thing that we use to create and manipulate this data, and alternatives to this exist, but are less commonly used. But why would we use one at all? Why not just chuck it all on a spreadsheet? Well, the reason for this is if you have a look at this image that I nabbed from Amazon, if you wanted to put all of that information into a spreadsheet, it would look nightmarish. So trying to scale up to something that's enormous, you're going to have issues with a spreadsheet. Additionally, if you're like us and have 128 million rows, there's no way that will load into Excel. So 128 million rows and about 1 terabyte. If you want to query that, you need something pretty substantial. Docker. Has anybody heard of Docker? Yeah? Okay. I would describe Docker best as a necessary evil. Do you agree? So Docker packages applications and their dependencies all into things called containers. Then you can you can grab this container, move it somewhere else, and then run that, and it will run just as it would when you packaged it. Which isn't really a very good explanation of why it's useful. So why use Docker at all? A container can be thought of very loosely as a literal container, where Docker is the thing that makes the big container, and all the stuff in it is the things that it's separated out. So if you wanted to ship a bunch of containers overseas, you don't want all of the cargo being mixed up, because then it's just a nightmare and things can conflict and break. So if everything's in a container, you can package it up, make sure it works, move it to whatever system you like, and know that it will definitely work on that system. So it's really good for testing consistency in deployments. Yeah, so the caveat with Docker is that containers are really heavy. So I get this quite a lot where Docker crashes because I'm trying to run 11 containers at once, which I would not recommend doing on a laptop. But if you're just running 4 or 5, it should be okay. The last thing is cloud computing. Cloud computing is enormous today, and it can be thought of just as the delivery of some computing service online. Things like security, AI, machine learning, networking, virtual machines, storing stuff. I'm sure most of us have some stuff on cloud storage, for example, but you can also store enormous files. There's also more things than this that you can store in there. Basically, if Google can charge you for it, they're going to try to. Why use a cloud computing service at all? Which is a very good question because it's really annoying to implement. You have to add a bunch of infrastructure and use that specific program to do it. But it turns out there are quite a lot of upsides to using something like this. So it doesn't matter how many GPUs you've got in your computer. I guarantee you Google has more. So if you need something done very quickly, you can do it. The example I showed earlier where we had like a terabyte table, processing through all of that took about 30 seconds. Network stability is a big one because our country doesn't have very good internet. So if you can outsource that to Google, for example, you're not likely to get any dropouts. Being able to access all of your things from anywhere is also pretty big. And that means that you can collaborate more easily as well. Inbuilt security is also a big one, especially if you don't want to end up like Optus or Medibank. because it's going to be way harder to break into, like Amazon, for example, than it is to this. Data backup is also pretty big. I mean, you don't have to worry about losing your data. If you drop your hard drive and it breaks, then all your data's gone. That's just not a thing, because massive companies have so many resources that they can duplicate the data at least once. Perhaps the most important reason, though, is feeding the corporate machine. Jeff Bezos wants your money. Yeah, jokes aside, I just think I would just like to end with a summary about all the things. Number one, if you're just trying to keep up with the data rate, free resources are available for everything. Learning a little bit can go a long way. These slides are going to be made available on Slack, and the next slide is resources. So have a look if you like. If you don't have the time to learn new things, dedicated research software developers are here to help. Just call out if you need. And the last thing, if you're interested in a career, non-developers can move into software development space. I like to think of myself as proof. Yeah, thank you. That's me. Are there any questions?
All right, thanks, Keegan. So are there any, we have some time for a few questions. Yeah.
Thanks, Keegan. One of the things I think I've noticed in the workspace is that a lot of the coding kind of competency comes about on the job. And of course, like learning any language, you learn things through immersion. And at the same time, on the flip side, when you're doing courses and things, you get a lot better grounding of, I guess, fundamentals and good practice, but you don't have that same immersion in actually solving a real world problem. And the result ends up sometimes being a bit of a mismatch between, kind of the basics and what you actually use. Have you had any experience in marrying those two things together, or any advice for others trying to do the same?
Yeah, I mean, I would definitely agree with the point that you're making. This may be a product of my time because, when I was going through high school, for example, there were very limited options for learning things about computer science. Even when I started doing physics, it was not really emphasized how to write code at all. You're just kind of expected to learn it as you go, as a means to an end. In terms of marrying the two, I think I think that each of them have their own space. Like in terms of solving real world problems, that's why people do like research projects and stuff as part of their course. And I think that's like the best place to sort of practice what you've learned in whatever course you were doing to learn about coding in the first place. I mean, I did an HPC, or high performance computing course in my honors degree, but like I never really had a way to practice that while going through my undergrad.
Ryan, just make sure all people at the back ask questions, so I have to walk all the way over.
So working at CIC, you obviously have a lot of interaction with academics from all works of Curtin. What are some, like, in terms of convincing academics to, a lot of them are very concerned about the protection of their data, or maybe they're working with a company's data and they're kind of worried about protecting their behind. Like a lot of academics are scared of going, well, not scared, but intimidated by going to cloud computing that they don't understand with confidential data. So do you have any comment on that you've learned from working with academics?
So unfortunately, I'm sort of on the opposite side of what you're talking about, because I work at the Curtin Open Knowledge Initiative, which is all about spreading our data. But yeah, what you mentioned is a good point. I think it's like sort of a communications issue. Trying to convince an academic why things need to be done the hard way and not the fast way is probably always going to be an issue. And for things like that, I'm glad I have, like, my line manager, for example, is an excellent project coordinator. So it might be a situation where you need sort of like a buffer in between somebody who's really tech savvy and somebody who just needs to write a paper, for example. But in terms of my own experience, I haven't really had that opportunity yet to sort of try to communicate directly with an academic like that.
Any other questions from the floor? Any on Slack? What are you doing, Verwin? I just have one question then. So I don't know what the job market is like for research software engineers presently, but I imagine it's only growing. So as someone early in their career, what's a good way to maybe how to explore this might be an option? Is there a community they could be part of?
Yeah, I don't know about a community. What I can definitely say is from my experience in the Curtin Institute of Computation, we've grown from like 6 members to about 40 over the past 2 years. So in terms of the space that the workforce occupies, is definitely growing. I think because it's sort of a young branch of software development, there aren't going to be any dedicated communities for maybe until it grows much bigger. But when I was applying for the job, I wasn't really applying to be specifically a research software developer. I just wanted to sort of increase my skill set by any means possible. And I ended up here because that was the best skill set that I had. So I think the way to sort of get to research software development is through research itself, and just sort of trying to specialize your skills towards a software practice.
Okay, thank you, Keegan. Please join with me in thanking Keegan for spending the time. All right, so that wraps up our keynote. I'm going to hand it back over to Daniela, who will close out our conference for us.
Thank you very much, Xixing. Thank you very much for the WA branch and for Keegan and for all the keynote speakers and speakers from today. It's been a great day and I hope you all have enjoyed. So I have exciting news to share. So let me share my screen. We have some results. I don't know if Xixing has his ruffle. I think we need some exciting noise before I announce. Do you? So let me share. Oh, my slide's not here, but I'll share the whole thing and then. I'll give it away the whole. Let me. Yeah. Can you all see my screen? Is it all good? So we have some prizes. Can you hear me? Xixing?
Yes, we can hear you.
Okay, great. So we're going to announce the prizes for the best presentations. So we have prizes for the 15 minutes presentations and for the 5 minutes and also people's choice. So if I could have some noise before I know. 15 minutes talk. So first place is for Jackie Chong, who presented today, and that's the Louise Ryan Award. Second place for Fiona Scarf, and third place for Betsy Williams. So please join me to thank them for their presentation and congratulate them for the great presentation. And we also have prizes for the 5 minutes. First place for Melissa Middleton, who presented the first day. Michael Mifiodovas, I'm sorry if I mispronounce any names, and Owen Forbes as well. So congratulations, guys. And people's choice is Jerry Zhang from today's presentation as well. All exciting presentations. We have an amazing number of good presentations, but you can only choose those 7. So if you haven't won, don't be worried. It was a tough task for all of us to score your presentations. And we thank our sponsors. So we thank SDAS for sponsoring the prizes for the 15-minute stocks and 5-minute stocks. And And we thank the SSA for sponsoring the prize for the People's Choice with the SSA t-shirt. If you don't know, like if you haven't seen it before, check that in our website and perhaps get one for yourself. It's pretty cool design from Ben. I forgot his last name, if someone can put it there. But it's a very cool t-shirt. Yes, congratulations everyone, and thank you so much for your talks. And I'd like to thank all our sponsors for this conference, that they made this possible with a very generous contribution. So we have MZ, and we have the ABS that contributed sponsoring the conference, but also sending some allowing the staff to submit some great talks and contribute to this conference as well. SDAS for sponsoring the prizes, and the SSA and NZSA, and also Curtin University for all the support in the background, and also sponsoring all the activities. So, and I also would like to give a special thank you for all those who contributed for this conference. This is a teamwork, a team effort, and I'd like to acknowledge everyone. And I'd like to acknowledge the organizing committee. From WA, we have Lucy and Shishing, we're very familiar with it now, and from New Zealand, G and Rory. And then from SSA, we have Jody, that helped a lot with the technical side of things and lots of ideas as well. She's the SSA events coordinator, and Marie-Louise as well from the SSA, who has been giving great support in the background. And I also would like to acknowledge all the volunteers that have contributed for this conference, that chaired sessions, that scored presentations, that did the social events like Melissa, and contributed for discussions. And I would also like to acknowledge the tech team that made the Slack channel alive, and it was Mark and John, guided by Jody as well in the background. So I really would like to thank them, and I would invite you to join me to thank them for their great work. And I'd like to acknowledge and thank also all our keynote speakers who made this conference very exciting as well. So Sama, who also did the workshop, and today James and Lisa as well for some great talks, for her great talk yesterday, and Keegan. So they all shared their knowledge and expertise and experience with us, and was awesome. The panelists as well, all of them that shared their expertise and what they think we should be thinking of when we pursue this career. So we'd like to thank them for giving their time and sharing their knowledge. And also the mentoring program representatives, Nicole White and Melissa Thompson. So don't forget to have a look at the information that we have in the Slack channel, and perhaps enroll for that program, which I'm sure will be beneficial for all of you and all of us. And I'd like to thank as well all the fantastic presenters and participants that made this conference possible, because we can have all the sponsors and all the organizations in the world, but if you don't have the participants to make this alive and an interesting conference, it wouldn't have happened. So I'd like to thank you as well for coming by and participating in the conference. And just a reminder from some exciting events that are coming up. So the Bioinformatics Summer Symposiums from MZ, so our sponsor. If you're working in this area, or if you're interested in learning more in genetics and bioinformatics and biostatistics, check out the website. And this information is also in the upcoming events channel from Slack. And they also have a free public lecture as part of this summer school. So you can join that. It will be online and in person in Melbourne on the 23rd of November at 6 p.m. by Dr. Drew Berry. So don't miss that. And I'd like to thank again all our sponsors and everyone for joining us. And let me stop sharing. Thank you very much, everyone. Thanks for coming, and keep the conversation alive in Slack. if you want to post your slides and if you want to post anything else and continue the collaboration, please continue to do so. The Slack will be live for 3 more months. So feel free to contact anyone that has been part of this conference. And remember, we have a code of conduct that even though the conference has finished, we need to abide by those. So thank you very much. It's been a pleasure.